for thinking about the Dirac setup. So Victor Ginsburg has introduced notion of Poisson vector bundles recently, a few years back, and we are trying to extend this idea from Poisson structure to Dirac structures. That motivation came because of this work. Eckhard Mencken has a notes that talks about some Poisson structures from the point of view of Dirac geometry. It says it will make it easier to work if I'm thinking of Poisson structures as Dirac structures. So this is serving two purposes. One is to think of Poisson vector bundles as Dirac vector bundles, and generalizing from Poisson setup to Dirac setup. And these to think about these two papers, the idea came from this work of Bursin, Drummond, and Neto. So this paper appeared in 2021. So there they introduced notion of Dirac-Nijenhuis structure as a generalization of Poisson-Nijenhuis structure. So it is in similar sense. We are trying to extend Poisson vector bundle to Dirac vector bundle. This can be seen as in some sense, a motivation to think about generalization. So let me quickly recall the notion of Poisson structure. I mean, this is Poisson geometric constants. I'm assuming many of you know what this is, but I'll quickly recall what it is. So given a smooth manifold, a Poisson structure is a binary operation on infinity M with following conditions. First condition is that this set have a R vector space structure, and we want this map to preserve the structure. In the sense, it is R bilinear. Secondly, whenever I think of a binary operation, the first thing that we'll be thinking about is it commutative, is it associative? So here it is not commutative, but up to a sign. There is a minus. If I interchange f and g, I get a minus sign. That's what I mean when I say commutative up to a sign. Next, associative also up to some small correction. It's not associative, which means this difference it is not necessarily zero. If I take three elements f, g, and h, if I take the bracket with the gh and then with f, it need not be same thing as taking bracket of f, g and then with h. So this difference is not necessarily zero always, but this is controlled by this quantity. This is again an element in say infinity m. So this is what I mean when I say associated to a correction. So the usual name for this is Jacobi identity, but for some personal purposes, I want to think in this sense. And the other structure on infinity m is the product structure. Given two elements here, I can take the product of those elements. I mean, they are maps from M to R. So the R has a product structure. So in any two maps would give me a product Fg from M to R. So this bracket preserves that. This bracket preserves that structure in this sense. So I can simply say that this is in some sense it is a derivation. I don't have to say what about gh comma f, because the previous operation says it has this property. So it suffices if I say the equality for this. So that's the Poisson structure. A basic example is on R2n. If I'm thinking of the coordinates as Q1 Q2 Qn and P1 P2 Pn, this is the basic example of Poisson structure. And the next example is coming from a Lie algebra. Given a Lie algebra, we are looking at the dual space set of all linear maps from G to R. So the bracket operation on G, that's the map from G cross G to G. This will induce a bracket operation on C infinity of G star. C infinity of G star, set of all smooth maps from G star to R. This would have as a subset set of all linear maps from G star to R. So if I'm thinking of double dual as G, so this can be seen as an extension of this this binary operation. So it's different in this sense. For two elements f and g, we have to declare what is the bracket. So f and g are smooth maps from G star to R. We have to declare the bracket f comma g from G star to R. So take some element theta. F is smooth map. I can take differential of f at theta, which is a linear map from G star to R. That is the element in the dual. Under this identification, I'm seeing this as element of the Lie algebra. Similarly, G star theta, the differential of G at theta, element of G of the Lie algebra. So these two elements would give, I take the bracket operation in G, an element in G. So theta is a map from G star to theta is a map from G to R. I evaluate theta here to get element in R. So this is the Poisson structure on G star. Now another way to think about Poisson structure is as a bivector field. I mean, for some people, this map itself is a bivector field. I mean, where is it? So this map is itself is a bivector field, but we are thinking in a slightly different way. A vector field we are thinking of as a map from that takes a one form with a smooth function. A bivector field takes two one forms with a smooth form. A multivector field takes multiple one forms and gives a smooth map. So these are all derivations in the same sense that I mentioned previously. So given a Poisson structure, one can associate a bivector field in the following way. So I should take two one forms. Maybe I can do just with this. I take these two one forms dfdg and I declare it to be the bracket of f with g. Now one can go from bivector field to Poisson structure in the sense, instead of putting this colon here, I can put colon here and declare it to be, start with the bivector field, declare f comma g to be this for every f and g. But for this bracket operation to satisfy Jacobi identity, we need a different point of view, different different setup to say when does pi when does the bracket operation coming from pi has the Jacobi identity. So for that I need to say what is the Schotten bracket. So it takes two multivector fields, gives a multivector field. The degree is declared in this sense. A k multivector field and L multivector field will give k plus L minus 1 multivector field. It is defined in this sense. So it should be just think of it as pq minus qp, but with you should be a little careful. Q will act only on the L elements. So I'm taking L elements and then the appropriate permutation, and then the remaining elements applying on P. Similarly, I start with P, look at first K elements, and then the permutations, apply P, and then the remaining on Q. So this is the bracket operation. I shouldn't say bracket operation, just shorten bracket. So so if I start with a bivector field, that means a degree 2. So 2 plus 2 minus 1. Okay. Maybe this is not necessary. So a Poisson vector field, Poisson bivector field comes from Poisson structure, will have this property. If I take the Schotten bracket of pi with itself, I get 0. Similarly, the converse also holds. If I start with the bivector field with this property, I get a Poisson structure. So now a Poisson structure can also be seen as a Morse of vector bundles from T star to Tm. So I'll quickly say in what sense. So by the very definition, it's a bivector field. So it takes two one forms and gives a smooth form. If I fix one coordinate, I get a map from omega 1 m to c infinity m. They are just vector fields. So that means I have a map from sections of the dual bundle to the sections of the tangent bundle. Not every section map will come from this, but this being c infinity m linear will come from a Morse of vector bundles. So it is in this sense a Poisson structure can be seen as a Morse of vector bundles. So if this is invertible, this is just a Morse of vector bundles. It not be invertible. If it is invertible, then we call it to be non-degenerate Poisson structure. A more general name for this is symbolic structure. So this is an attempt to motivate the notion of Dirac structure in the following way. So a symbolic structure on a manifold is a non-degenerate Poisson bivector field. Because it's non-degenerate, which means this is a invertible map. So I can take the corresponding inverse also. So I can think of Tm to T star m. So this should remind you the notion of a two form. A two form takes one vector field and gives a one form. So it is in that sense, it's a two form I have mentioned here. So ignoring non-degeneracy, similarity structure will give two notions. One is Poisson structure, one is pre-similarity structure. Both of them are modes of vector bundles, but in other direction. In the sense, this is from T star M to Tm. This is from Tm to T star M. So a Dirac structure should be seen as a generalization of these two setup. So as I said, this is all motivated from. I mean, one motivation is this paper of Eckhard-Mankin. So it says one advantage of looking at the data structure it's more about flexibility. One can think of pullback maps and other structures in a more nicer way when I'm thinking of in the Dirac setup. So it is this is one reason why we are trying to extend from Poisson setup to Dirac setup. So now we have two structures in the sense of maps. We want to generalize them. So one way to compare two maps, say observe that these two maps do not have same domain, do not have same codomain, but there is there seems to be some relation. So one way to compare these two is to look at the corresponding graph. Both of the graphs are subsets of A cross B. So here one can compare or look for a generalization. So for Poisson structure and for the similarity structure, we are looking at graphs. This will be subbundle of the direct sum. So all I'm doing is I'm starting with a one form, looking at pi of that and the one form. So this element in here. Similarly, start the vector field. I'm starting with the two form. So omega x is the one form. So this is an element here. So it is in this sense we are trying to look Poisson structure and similarity structure in a as part of a single setup. Now the question is which property of these two do you want to compare and generalize? So to do that, one needs notion of this is not a correct word to use. It is, but just for time being, I'm using this word. So for any vector space V, one can come with this operation on the direct sum. V direct sum V star to this. I'm thinking of the one vector space. So I take an element here, that would give an element here. So I'm evaluating F at W and G and on V. This gives the map. This gives this following map. One can do the same thing by replacing this vector space with the tangent bundle. I'm starting with a vector field and one form. This I'm treating as a single element of this setup. So I take two such elements. I evaluate in this sense. Here I'm getting R, but here I'll be getting. I mean, for each element M, I'm looking at this setup. So for each element M, I'm getting an element in R. That is a smooth function. So this is the extra structure that I want to use to compare these two. By the very definition, these two graphs are maximally isotropic with respect to the structure that I mentioned previously. What is maximally isotropic? If I take two elements from the same from this graph, the 645. The bracket operation will give 0. That is mainly because pi and omega are skew symmetric. So it is for that purpose. For that reason, we get 0, and one can check it's. So this only means it's isotropic, but one can check that this is maximally isotropic. So one terminology, a subbundle that is maximally isotropic is called a Lagrangian subbundle of the direct sum. Now a Dirac structure, which I mentioned as generalization of symplectic and Poisson structure, should have this property because that is one common property between these two graphs. So that is the first condition. The subbundle should be Lagrangian subbundle and some integrability condition. To talk about this integrability condition, we need the notion of coherent bracket. So this bracket operation is on the sections of this direct sum. it takes an element x alpha, y beta, and declare in this sense. This vector field setup is just the Lie bracket, and this is some nice combination of uh, Lx, Ly operations and the extended derivative. So a Dirac structure on the manifold should be seen as a subbundle that is maximally isotropic and involutive with respect to the current bracket and the inner product. So now we want to extend. So maybe this I'll ignore now. There is no time. I'll quickly say why Poisson structure would be a Dirac structure. Poisson structure as a bivector field. This I have shown that it has the maximum isotropic property, and to check the involutivity, it is sufficient to check this bracket that for 3 elements A1, A2, A3, if this bracket is 0, then it is a Dirac structure. The same thing for similar structure. The graph is already seen to be maximally isotropic. Now to check the involutive property with respect to the current bracket, it is sufficient to check this bracket operation. And this bracket operation is just d omega of the 3 vector fields, because omega is pre-symplectic, d omega is 0. In this case, because of the bracket being Jacobian, has property of Jacobianity, this bracket plus the permutation is 0. So it is in this sense, Poisson structure and similarity structure are Dirac structures. Another example is, you start with the foliation. It's an integral subbundle of the ensemble. And look at the annihilator. What is annihilator? For a very vector space, V annihilator is elements in the dual such that when I restrict the element to the subspace, I get 0. So I can do the same thing for every element M, and where M over elements of M, and that would give me a subbundle of the dual bundle. So now I'm taking the direct sum. So this is maximally isotropic by the very definition, and the involutive property of the foliation would imply the direct sum is also involutive. I'm using same word here, but this is with respect to the Lie bracket, this with respect to the current bracket. So this is an example of Dirac structure. Now this is just I am trying to say that many people have done many generalizations from Poisson setup to the Dirac setup, and these are one of the motivations for me to do. So there is no number Poisson structure, and there is a corresponding Dirac structure generalization not very long ago. Similarly, the Poisson structure on manifold was generalized to Poisson structure on Lie algebraids, and then there is an extension from Poisson setup to Dirac setup. Here there is a Poisson sigma model. This was generalized to Dirac sigma model in 2005. The Poisson Lie group was generalized to Dirac Lie group. There are 3. I mean, there may be many other works also, but I only know about these 3 works. Then the recent one, 2022, is a Poisson Nijenhoff structure. It was generalized to Dirac Nijenhoff structure. So these are all in some sense related, but not exactly the same. So these are the attempts in generalizing from Poisson setup to Dirac setup. So in this work, we are trying to extend from Poisson vector bundle or Poisson manifold to Dirac vector bundle to Dirac manifold. So this I am expecting to finish in 2023. So and we are also trying to extend. There is no Poisson carry, an invariant associated to Poisson manifolds. We are trying to extend the same thing with the Dirac setup also. Now, because of the Poisson vector bundle, the base manifold is has a Poisson structure. So start with the manifold with the Poisson structure. Poisson vector bundle over Poisson over this Poisson manifold consists of a vector bundle and an extra map that takes a smooth function and a section is a section. We want this to have some condition. First condition is if I fix one coordinate, I can think of it as a map from gamma p, sections to sections. So that is this map. Observe that for any vector space, this will have a Lie bracket. So this is a Lie algebra. We already know CNTP also has the Lie structure by the very notion of Poisson structure. So we want this map to be Morse of Lie algebras. Secondly, this is not P doesn't, I mean, the structure on P is not just this being a Lie algebra. There is a product structure compatibility also. So we are just writing down the compatibility conditions for the product structure. So this is the notion of Poisson vector bundle. Now, whenever we see this version, so this should remind you the notion of representation of Lie algebra, and that is the first example. So start with the Lie algebra, take any representation, and look at the trivial bundle. G star V2 G star. This vector bundle can be turned into Poisson vector bundle by giving this map. So I should give a map from that takes smooth functions and section. But here, because this being a trivial bundle, sections are just maps from G star to V. So that is just this. So this bracket operation gives a Poisson vector bundle structure on this trivial bundle. Next, start with the Poisson manifold and look at any vector bundle. We are looking for a map of this form that takes a smooth function, take a section, gives a section. But what we are familiar with is of similar type that takes a vector field and a section gives a section. So this is what is connection. But thanks to the Poisson structure, there is a relation between infinity P and the vector field by this. So start with the connection. Look at this map and just take the corresponding composition. That would give a map from here to here. But this is not in general doesn't have the property of Poisson vector bundle. Suppose this delta is flat, then that would give that this delta is flat would make this into a Poisson vector bundle. I have 2 minutes. I'm trying to finish it. So Poisson vector bundle. I mean, how do you generalize Poisson setup to Dirac setup? It is not very straightforward. How to generalize this definition? So it is for that purpose we are seeing Poisson vector bundle in a different sense. So we are seeing this as a representation of the Lie algebra. Okay, that I'll say later. But Poisson structure can be seen as the Lie algebra structure on the dual bundle, and Dirac structure can also be seen as the Lie algebra structure on this sub bundle. So it is in this sense we are trying to generalize. So this I'm not saying Lie algebra definition. It's just a vector bundle that wants to behave like tangent bundle and has the external structure of Lie bracket with the compatibility condition. So now a Poisson structure on the manifold comes with this Morse vector bundle and with this bracket. So and the compatibility between this Morse vector bundle and the bracket operation on one forms. So it is in this sense we are seeing Poisson structure as a Lie algebra structure. So Poisson vector bundle on Poisson manifold, we want to think of this in a different sense. But Poisson structure is Lie algebra structure. So it is in this sense Poisson vector bundle should be seen as some geometric structure on Lie algebra, and this geometric structure is what we are seeing as a representation. So because of the time is up, I'm not mentioning this extra details. But yeah. So this is how we were trying to see representation of this dual bundle is just Poisson vector bundle on the Poisson manifold. So this is what we are trying to generalize. Given a Dirac structure on the manifold, a Dirac vector bundle is just a representation of the Lie algebra. So by the very construction, every Poisson structure, Poisson vector bundle will turn out to be Dirac vector bundle. And we are also seeing some examples that I don't have time to explain now. And there is a notion of similarity vector bundle and qualitative vector bundle. These two are Dirac structures But these notions doesn't seem to be giving the Dirac vector bundle setup, because in there the structure is on the top manifold. So, but for us the structure is on the base space. So it is in that sense they are slightly different. And we are expecting that this notion is related to the generalized holomorphic vector bundle structure studied by Iko Wang and Gualteri. So this was the main idea. This was the main intention to talk about generalized structure vector bundle on the generalized complex manifold. So because Dirac setup is seen as a starting point towards generalized complex structure, we are starting with this. And thank you. Time is up. So Praphulla, thank you so much.
Thank you, Praphulla. Are there some questions?
Yes.
Oh, yes, I have a quick question. So for your definition of Poisson vector bundle, are you assuming constant rank, or does this work for example, foliations that are singular? So I'm just curious to.
No. Singular foliations, I'm a little bit afraid. I don't know. I'm reading now. So for now, everything will have same dimension. So that is what the starting point is. I'm trying to extend. I mean, once I know enough about the singular foliations, I'm trying to extend it. But for now, everything is regular only.
Okay, thanks.
Yeah.
Any other questions? Oh, Carlotta.
Hi. So if I understand correctly, your notion of Dirac vector bundle is basically a Lie algebroid representation of the Dirac bundle as a Lie algebroid.
Yes.
And so having studied those exact objects myself, I'm curious sort of what direction you are planning to take this in.
Actually, the Ginsberg's idea is to come up with a new invariant for Poisson manifold. The Poisson cohomology is already there. It's an invariant, but it was difficult to compute for Poisson, even for the very basic examples. So he said we are extending it to Poisson vector bundle and the Poisson K-ring. So I am hoping one can come up with a similar invariant for Dirac setup also. But this is only starting point, so I cannot say much details as of now. So that is the intention. We're coming up with notion of Dirac vector bundle, and leads towards the generalized complex structure, and also look for some invariant setup.
Okay, then I'll just maybe say two things there. So that you might want to look at. So there are publications in particular by Yvette Kosman-Schwarzbach that already deal with some of this stuff. So in case you're not aware, you may want to look those up.
Okay. Thank you so much. I will check that.
Okay. Thank you so much, Praphulla.